Hey there, hi there, ho there, welcome to Unit 6, Volcanoes. There's my volcano dance. Let's jump into it, shall we? I really don't have much to say. Let's just jump into this. In fact, you know what? Let's start it off with giving you the first part of the super secret code. It is the number 1. Why not, right? The number 1. One more time, the number 1. So just some volcano basics. So what is a volcano? I think we have an idea of what it is, but simply stated, for purposes of defining a volcano is any opening in the Earth's crust through which lava, ash, gases, and or Earth's internal heat escapes. So there's more that comes out of the Earth than just lava. In fact, that's often not the case. So when any of this material escapes, this is the technical definition of an eruption. It's usually a combination of those things. An eruption itself can be explosive, one large, massive explosion, sending material high up into the sky, ash and gas up into the sky. It can even, coat the whole atmosphere with ash if it's big enough. Or an eruption can be quite calm with gentle flows of material. Oftentimes, if lava is being erupted, it's actually pretty gentle. Lava flows kind of like water, and it's often associated with more gentle eruption. It's that ash and gas and other stuff that you got to worry about. That's usually what causes the bigger explosive volcanoes. Not all volcanoes are the same. They have different processes in formation, and that all goes back to the different tectonic settings and what drives plate tectonics. And that's why we started this class, a few weeks back, talking about plate tectonics. So, the process that drives plate tectonics is also the process that is either directly or indirectly the cause of volcanoes, and that's mantle convection. So, because Earth's internal heat, that heat is transferred to the mantle, the convection process occurs where hot mantle material is rising, and as it cools down, it sinks. Remember, the mantle material, it's not liquid, it's pretty much solid, hot, sticky Play-Doh mixed with rocks, but it does have some flow to it. It does move. So that's not like where the volcanic material comes from. That's not where like lava and stuff comes from. It doesn't come from the mantle. But the process of mantle convection helps to feed and create volcanoes. So, again, mantle convection, either directly or indirectly, the cause of volcanism. Whether at, kind of divergent boundaries or convergent boundaries, or hot spots, or any number of things. What typically happens is mantle plumes are somehow melting the lithosphere, the upper mantle and the crust, and it's that material that is melted, the solid crustal material that's melted, that bubbles its way up. So just to get a couple more definitions out of the way. So when we're looking at a volcanic eruption, very cartoony. Molten rock, hot molten rock that's been melted from the crust, not from the mantle, but the mantle just transfers heat to kind of the upper parts of the mantle or crust, and it's that stuff, the lithosphere, the hard stuff that melts and eventually works its way up. So in that liquid molten state, this liquid molten rock underground is known as magma. Magma is molten rock below Earth's surface. That very same stuff, as it makes its way up and out onto the surface, the very same stuff, as soon as it reaches the surface, it's called lava. So lava is molten rock above the Earth's surface. Two different names for kind of the same thing. It's just determining on where this material is at. So down here, this liquid molten rock is magma, lava. Two different names for the same thing. So again, where does magma come from? What is the origin of magma? As mentioned, it's small little pockets of magma form from the melting of tiny regions of the mostly solid upper mantle and or crust. So it's not it's not, so liquid magma is not coming from the liquid outer core. It's not liquid molten rock, does not come from the liquid outer core. It does not even come from the mantle. The mantle causes melting in at or near the crust or just below in the upper mantle. And it's this material that's melted that bubbles up and possibly sometimes out. So that's where the magma and or lava is formed. Against the melting caused by all that heat brought from the core in the process of mantle convection. So, depending on where this melted stuff comes from, will determine the type of volcano. There's a number of different types of volcano, and the type of eruption that will occur if there is an eruption to occur. And that's dependent on where this magma is originally melted from. Lower down towards the mantle, higher up in the crust, where is it coming from? So, there's 3 different types of magma, molten rock below ground, and it's really determined, again, where this melted stuff is coming from. The mantle convection is transferring heat from the core up towards the crust, melting material. But where is that melted material coming from? Because where we're melting the stuff will determine the type of magma based on silica content. Silica, as we saw last unit when we were talking about minerals and rocks, silica, well, the most common form of silica is a mineral called quartz. Different varying amounts of silica, like quartz and some other silica-based minerals, how much or how little of that stuff will determine the type of magma, which will also then determine the type of volcano, which will then also determine the type of eruption. So, from the lower regions of where magma is coming from the kind of upper regions of the mantle, we get something called basaltic magma. Basaltic magma is usually darker in color. It's made up of heavier materials, heavier elements. From the kind of boundary between the crust and the upper mantle, or at that boundary where the upper mantle meets the crust, we usually get some basaltic, but maybe more andesitic magma. It's kind of like an in-between from the lower basaltic magma and the crustal melted material, which is typically rhyolitic in nature, rhyolitic magma. Rhyolitic magma is usually made up of the lightest elements. So the basaltic magma from lower down in the upper mantle, usually heavier elements. So it's heavy in iron and magnesium, whereas rhyolite has more proportion of lighter minerals like oxygen and silicon. But again, it's where this stuff is melted that would then determine the type of volcano, which would then determine the type of eruption. So when we're looking at these 3 different magmas, basaltic, andesitic, and rhyolitic, we need to talk about a term called viscosity. But you know what? Before we do, let me give you another part of the super secret code. It is the number 4. One more time, the number 4. Heck, let me give it to you one more time. The number 4. Viscosity is defined as the resistance to flow. The more viscous something is, the more it doesn't want to flow, the more resistant it is to kind of flowing somewhat like a liquid. Maybe you've heard this term. Oftentimes it's used for motor oil. Like if motor oil has a low viscosity, that means it very easily flows. It has a low flow to it, and it causes, things to move smoothly in your car engine. Whereas something with a high viscosity, it's very slow moving and sticky. Thing like cold honey. So the viscosity of magma, in this case, is affected by the composition. As silica content increases, the more quartz and other minerals similar to that. So the more quartz that's melted into this magma, the viscosity increases, meaning it gets more sticky. The less silica it has, the less quartz and similar minerals it has, the more flowy and runny it is. So the main difference between basaltic, andesitic, and rhyolitic, again, really comes back to how much of the silica content, like quartz, is in there. How much of it got melted from that surrounding upper mantle or crust. So again, that affects the flow of the lava, where it's nice and runny, if it comes out, or if it's more slow moving and sticky lava. And that goes into affecting also the shape of the volcano. So for magma, we have to worry about viscosity. Is it runny or is it kind of slow and sticky? And then volatile content. Volatiles is just a term for kind of free gases floating around inside the melted stuff, like H2O, which is water, so like water vapor as a gas, or carbon dioxide. If magma has a lot of volatile content, a lot of gas kind of just naturally in it, the more gas, the more explosive more explosive that magma and lava will be, the more explosive that volcano is. So it determines how explosive the eruption will be. So viscosity and volatile content, two things we need to worry about. As volatile content increases, so as the amount of gas in magma or lava increases, it increases the. I'm going to say that back. The amount of gas volatiles in magma increases as the amount of silica increases, because as silica increases, the viscosity increases. Meaning, more silica means the magma is more slow and thick. It's not as flowy. So if it's, think like cold honey. So a high viscosity magma is very thick. So if you get any gases in there, it's really going to trap gas bubbles in there because it's really sticky, slow-moving stuff. If there's less silica, the magma in lava is a little more flowy and runny. Bubbles go in, but bubbles can kind of just come right out. So there's not a high volatile content. This image describes all of that. If you can understand what's going on here, you can pretty much understand a lot about how the different types of magma create different volcano types and what kind of eruptions there will be. So basalt, kind of lowest on the silica content, it's known as a mafic igneous rock. It has a very low viscosity, so it's very runny. So it has a very low volatile content, not a lot of dissolved gases in it. So it's not very explosive, and it forms these fluid, runny, big shield volcanoes. It's typically lava coming out of here, very runny, because it's low in silica, very low viscosity, and it doesn't explode out because it doesn't have a lot of gas trapped in it. So usually it forms these shield volcanoes, very broad, very flat, very big, because these just erupt a lot of lava. Rhyolite, on the other hand, is high in silica, so therefore high viscosity, very sticky stuff, trapped a lot of gas content, therefore the highest explosivity type volcanoes will have rhyolitic magma. Super volcanoes are typically rhyolitic magma. The sticky stuff just builds up so much pressure because it doesn't want to flow and it's trapping all this gas, and then andesitic magma is usually considered right in between the two, intermediate in stickiness and viscosity and content. So it can form explosive volcanoes, a type called stratovolcanoes. We'll explain all of these types of volcanoes in later sections. But if you can kind of wrap your brain around this chart, you're doing good. So, different boundary types give us different geologic settings to give us different magma types and eruption behavior. So, convergent boundaries, typically explosive, just due to the type of magma that can be created, andesitic and or rhyolitic. Sometimes you can get basaltic gentle eruptions. Divergent boundaries, typically gentle eruptions. You're typically basaltic, low silica, low volatile content, flowy stuff. Hot spots, depending on whether they're under the ocean or under continental crust, can really be hugely different. Whereas a hot spot under the ocean typically forms basaltic magma. These are very gentle eruptions. Think Hawaii. Hot spots under continental crust are rhyolitic, high viscosity, high volatile content, very explosive, supervolcano type stuff. So, convergent boundaries, ocean to continent, explosive, continental hotspots, very explosive as well. One more part of the super secret code, the number 7. One more time, the number 7. Heck, one more time, the number 7. Pause here. When we come back, we'll talk about where volcanoes are located. See you in a minute.